My dear friends, today I'll discuss with you about the push-pull amplifier and as well as the power amplifier. Before going to power amplifier or push-pull amplifier, it is important to learn about some basic terms and definitions. First of all, what we mean by multi-stage amplifier. Multi-stage mean we are having some stages to amplify the signals. Okay, to amplify the signals. The input signal which is applied, at here. Okay, which is applied here. This is a multi-stage, okay. It's generally very small, a few millivolts, like that, maybe few millivolt. Therefore, the first few stages, like this one or this one, of a multi-stage amplifier handles the small signals, very, very small signals, and have the function of only voltage multiplication. However, the last stage handles a large signal, and its job is to produce a large amount of power in order to operate the output device, that is like a speaker, right? So, small signal amplifiers, this may be a small signal amplifier, and this type of amplifiers handles small input AC signals. And then we are having the last stage amplifier, like this one, push-pull. Okay, voltage amplifier generally fall in this class. Voltage amplifier mean like maybe it is a small signal. Small signal is oftenly generally called voltage amplifier. The small signal are designed to operate over the linear portion of the output characteristics, like this is the output characteristics. And small signal amplifiers generally having a Q point at the center of the line, right? Therefore, the transistor parameters such as current gain, input impedance, output impedance do not change as the amplitude of the signal changes. So I'm talking about the small signal amplifier. Such amplifier amplifies a signal with little or no distortion. This is the characteristics of the small signal amplifier. So then we are coming to the large signal amplifiers. Large signal amplifiers are those amplifiers handle large input AC signals, and it may be few volt, right? And are called large signal. Mean if the input signal is few volt, that mean that amplifier is large signal. If it is milli or microvolt, that is small signal. Power amplifier falls in this class. Okay, power amplifier mean the input signal is of few volt. Large signal amplifiers are designed to provide a large amount of AC output power so that they can operate the output device like speakers. The main purpose of the large signal amplifier or power amplifier are the circuit's power efficiency, the maximum amount of power that the circuit is capable of handling, and the impedance matching to the output device. And it may be noted that all large signal amplifiers are not necessarily the power amplifier, but it is safe to say that most are. Okay. In general, what amount of power in volts? That's the question. The amplifier, okay, So this type of amplifier terms as the power amplifier. Now this is a comparison of voltage amplifier and power amplifier. Beta mean current gain for common emitter configuration. Voltage amplifier having very high, power amplifier having 5 to 20 low. Current gain is low here. The RC which we use, okay, mean now the output resistance from where we draw the output is a high 4 to 10 kilo, is low 5 to 20 ohm. Coupling, usually RC coupling and invariably transformer coupling. Input voltage here low, few millivolt, here high. Okay, collector current low, approximately 1 milliampere, is a high greater than 100 milliampere. Power output is here low, it is here high. Output impedance here approximately 12 kilo ohm, very high, and here very low, that is approximately 200 ohm. Now we're coming to the output, the power. What is the power available at the output of this amplifier? How much power is available, right? So an amplifier converts DC power drawn from the DC supply VCC into the AC output power. The output power is always less than the input power because the losses occur in the various resistors present in the circuit. For example, so consider this RC coupled amplifier. So this resistor R1, R2, RC and RE. So there will be the losses by the formula I square R. Whatever the current flowing like I1 is square multiplied by R1, that's the heat loss at R1. Similarly, heat loss at R2, heat loss at RC, heat loss at RE. So all these losses appears as heat. So therefore, that's why the efficiency becomes less, very less for an amplifier. And whatever the heat produced also increases the temperature of the circuit. This is again a problem. Now, what is the output power? Appears at here. Power is equals to VL. It is RMS value of the voltage. I'm talking about the output AC power at here. VL is the RMS load voltage. V square divided by R mean RC. What is the power, AC output power at here? V square upon R. Okay. I'm coming class A power amplifier. Class A power amplifier. So this is a very simple circuit. Now this is a load line, AC load line. Now in case of class A amplifier, the collector current, this is a collector here, this is a collector. The collector current flows at all the times during the full cycle of the signal. Okay, when the signal arrives here, okay, then the collector current, it flows at all the times for this signal. then it is known as class A amplifier. So this power amplifier is biased in such a way that no part of the signal is cut off. Mean like this is the signal. With this signal, you know what happens? There is a change in the voltage which is across collector and emitter and collector, which is across emitter and collector. So this is a signal. Okay, with the input signal when arrives here, there will be a swing in the collector emitter voltage, and with the swing in collector emitter voltage, there will be a swing in the collector current, like this. So our biasing circuit is such, mean VCC supply R1, R2 and RE. The biasing circuit is such that no part of the signal is cut off. Note that the collector has a transformer like this one. The collector has a transformer. This transformer acts as a load now. Okay, this transformer acts as a load, and which is the most common for or class of the power amplifier. The use of this transformer permits impedance matching, resulting in the transference of the maximum power to the load. Mean with the help of the transformer, we can transfer power from collector to this device. So this is a function of the transformer as a load. Okay, so this is here the class A operation. The operating point is so selected that collector current is flowing at all the times of the applied signal. So as the output shape is exactly, this shape is exactly as that was the input signal. Okay, therefore such amplifier have least distortion. So there is no distortion in the signal. However, they have the disadvantage. What is the disadvantage of the circuit? That the low power output and low collector efficiency, about 35% maybe. So this is the disadvantage. Now you know what is the maximum collector efficiency. You know here, what is the maximum VCE? VCE peak to peak. Okay, VCE mean the voltage which develops here across collector and emitter. How much it is? It is VCC. Okay, so what is VCC? Now we coming the class B power amplifier. In case of class B amplifier, the Q point is chosen at here. What happens when the Q point is chosen at here? In class B operation, the transistor bias is so adjusted that zero signal collector current is zero. Zero signal collector current is zero. What it mean? Mean when no input signal. This is input signal. Okay, when no signal is applied to the transistor, then there will not be any collector current. Collector current will be zero when there is no signal. That means transistor is, you can say, like transistor is off. Now what happens? So during the positive half cycle of the signal, the input circuit is forward biased. So when the positive half comes, then transistor, goes to the on state. Okay, but during the negative half of the signals, when positive half comes, again. Now in case of class B amplifier, this is very important. The transistor bias is so adjusted that zero signal collector current is zero. That means when this is signal, okay, when signal is not applied to the transistor, then the transistor remains in the off state. Next, when the positive half of the signal arrives, it makes the input junction forward biased, and then the collector current flows like this one. Input signal come, when the positive of the signal comes, only then the transistor goes to the on state because its input junction becomes forward biased. Okay, but when the negative half comes, input junction becomes reverse biased. Then the transistor goes to the cutoff region. In the off state, no current flows. So there is no collector emitter voltage and there is no collector current. Again the positive half comes. The transistor goes to the on state because its emitter base junction becomes forward biased. So this is very important. In the absence of the signal, there is no collector current. Transistor remains in the off state. When positive half comes, transistor works and there will be the collector emitter voltage and the collector current. When negative half comes, again the emitter base junction, the input junction becomes reverse biased. Transistor goes to the cutoff region and no collector emitter voltage appears and no collector current, right? Now in class C amplifier, Q point is here. In class B it was at here. In class C it is at here. Now when the input signal comes, then when the input signal comes, what happens? Now from here to here, there will be clipping. Only small part of the signal appears in the output. So output signal is less than 180 degree. Some part is clipped, okay, if the Q point is at here. This is called class C amplifier. In class C amplifier, the base is given some negative bias. so that the collector current does not flow. Mean for class C amplifier, input junction is made reverse bias slightly. Okay, when the input signal comes, positive half comes, some part could not appear at the output because of the reverse biasing. But when input signal becomes more positive, then input junction becomes forward biased. And then the transistor works, and then that signal appears in the output side. When the positive half signal starts, okay, so such amplifier never used for power amplification. However, they are used for tune amplifier, that is to amplify a narrow band of frequencies near the resonant frequency. Okay. Now this is the push-pull amplifier. Push-pull amplifier, we are using, first of all, this is the primary of the transformer. This is the secondary of the transformer. At the secondary, at the two ends of the secondary, two transistors are connected. Both are PNP, and emitter are connected together, right? And output, at the output side, there is again a transformer, and the output device is a speaker. The push-pull amplifier is a power amplifier and is frequently employed in the output stages of the electronic circuit. It is used whenever high output power at high frequencies is required. So two transistors T1 and T2, they are placed back to back, mean input or emitter are connected together, and collector, they are at the output. Now the load is type of a transformer. Okay, so the two transistors, they are set to connected back to back. Both transistors operate in a class B operation, mean one transistor works only for one cycle. This transistor works for one cycle. This transistor also works for one cycle. Okay. When the signal comes here, because of the mutual induction, let positive part appears here and negative part appears here. When positive part appears here, this is transistors P, N, P. This becomes forward bias. This will conduct. And at that time, because this is a base and negative part of the cycle, so this is in the off state. Okay, so one transistor conducts, other remains off. Now next, okay, when the next instance, what happened? At the next instant, here comes negative and here becomes positive. When here becomes negative, this transistor goes to the off state. When here it is positive, then this will conduct. So at a time, one transistor will conduct. Okay, so here the current is flowing like this. When it is in a conduction state. When it is not in conduction, no current. When in conduction, the current flows like this. Okay, when this is in conduction, the current flows like this, like in this way. So this is how the working of the push-pull. One time, one transistor is the amplifier. That in class B amplifier, the output appears only for one half of the input signal. So this is a load line. Okay, this is a Q point. Along x-axis it is collector emitter voltage, and maximum collector emitter voltage is equals to, at the Q point, it is equals to VCC. Along y-axis it is the collector current. So now the collector emitter voltage varies because of the variation in the voltage of the input signal. So input signal makes the collector emitter voltage to swing like this. Okay. Now, one thing keep in mind that as this voltage is going to more negative, है ना, तो collector current is the reciprocal of it. Then collector current will increase, and when it is going to increase, when collector ammeter voltage is going to increase, then collector current will come down. Now when collector ammeter voltage is becoming more positive, because the Q point maximum voltage is here VCC, and it is going to more increase, but it is a limitation that collector current cannot increase further, because collector current is a reciprocal of it. As it is increasing further, collector current cannot increase. Okay, so there is no collector current now. There will be no collector current for this part. Again the collector current now, it will start, because it is going to more negative, the collector current will start increasing, and when it is increasing, the collector current will come down. Okay. Now we will find what is the average current flowing in the output, because only one half of the signal is appeared at the output. So the total voltage of the one half cycle is calculated from 0 to pi, because pi to 2 pi there is no cycle. But we have to divide this total by 2 pi for making the average current. Okay, from 0 to 2 pi the average current is the numerator, total voltage 0 to pi divided by 2 pi. Okay. Rest of the mathematics is very simple. You just follow the steps and you will find it. Now you know that there is a relation between RMS root means K value of current with the peak value of the current, that it is peak value of current divided by root 2, that becomes the RMS current. Similarly, the RMS voltage you can find by using the same type of relation. So this efficiency is very good, 78.5. Today I am going to discuss the push-pull amplifier. Now what is the meaning of push-pull? When some part of the circuit is active, then that is, its output is going to high, then we say that the output has been pushed to high. And now after some time, If another part of the circuit is activated and the output goes to 0, then we see that output has been pulled to 0 or low. That is the meaning of push-pull. Okay? Now this is the primary of the transformer. This is the primary of the transformer P1, P2. And there is an iron core that the coil is wound over the iron. This one is the secondary. Now, at the end of the secondary, there will be the signals which are the out of phase. Because the transformer, the secondary of the transformer, it is a phase splitter, and one part of the signal is applied to one transistor, the base of one transistor, and other part of the signal is also applied to the base of the second transistor. Emitter of the both transistors are connected together, the NPN transistor, and then the grounded. And at the collector is attached, collector of both the transistors are attached with the primary of the output transformer. And the supply to the transistors given through VCC, and output is taken across the secondary of the transformer where RL is attached. Now the current flows anti-clockwise here, IC1 through transistor T1 and clockwise through the transistor T2. This is a positive part of the signal when arrives here, and negative part of the signal arrives at the lower transistor. Here the signal is coming, input signal. Signal is arriving at the primary of the transformer, and because of the mutual induction, the sign comes here for plus minus. And the base of the upper transistor becomes positive. If the base is positive, the transistor T1 works and gives the current as shown, and the lower transistor at that time remains off because the base is at the negative, because base is P is negative, the lower transistor is off, upper transistor. And for the another cycle, this is the current when the upper is high, and at the same time the lower transistor is off. So when the other part of the signal comes, what happens? The lower transistor, the positive comes at the base of the lower transistor, and then the lower transistor becomes high and the current starts flowing clockwise IC2, and at that time the upper transistor becomes off. So this is exactly class B operation. So the transistor is working for one cycle, this exact class B operation, because there is no current flowing in the absence of the signals. So let we write IC1. It is the sum of the DC current plus the AC currents with the harmonics, like 2 omega, 3 omega, they are the harmonics. They are mixed in the signals. Now, for its complete explanation, you go to my previous video, harmonic distortions. Now, as the second current is there, but it is out of phase. Out of phase means pi degree it is leading to the IC1 of every harmonic is leading by pi because of the phase change of pi. Now here we are thinking that this is a general equation. If some DC current, collector current also flowing, if it is exactly class B operation, then there will not be any I naught. Then there will be only the signal currents like omega 2 omega 3 omega. But here I naught is also considered if we are thinking that some current is also flowing in the absence of the signals. So because IC1 and IC2 flows in opposite directions, therefore output transformers through the output currents I naught in the secondary of so the transformer will be proportional to the difference of the two currents because the currents are flowing in opposite directions. So we are having I naught equals to constant and IC1 minus IC2. So upon subtraction, substituting the value of IC1 and IC2, we got that omega t, 3 omega t, 5 omega t, 7 omega t, all the odd harmonics are present now. Even harmonics are missed. So that is the advantages of the push-pull connections that the even harmonics are eliminated. There is no 2 omega, 4 omega now. Okay, this will happen if the two transistors are identical. Keep in mind this thing also. The two transistors should be identical. You know, actually, the collector current consists of the signal frequency and the higher harmonics are always present, but push-pull connections eliminates the even harmonics. This is very important. Now again, class B push-pull, the better arrangement is, the better circuit is as shown below. Push-pull, class A push-pull is rarely used because of low efficiency. To increase the efficiency as well as the output power, class B push-pull amplifier is used because as for efficiency it is very good and as well as for the high output powers. When no signal is applied to class B push-pull, then the collector current will be zero. There is no dissipation of the power in the absence of the signal. And dissipation of the power increases with the increased input signals. You know, as well the average current in class B operation is less than that in class A operation. For detail, you go to my previous videos for class A, class B amplifiers. Hence, power dissipation by the transistor is also less in class B operation. Now this is the circuit diagram for the class B amplifier. Here we are using the PNP transistor. This is very important. We are using here PNP transistor. Of course, you can make the connection with NPN also. But battery placing should be proper, as shown in the figure. There are the register R2, R1 for the biasings. The biasing is given that for some current flow in the absence of the signal, some very small current flows. This explanation is given above, how that it is push and pull. One is active and other is off, then other is active, then first is off, push pull. So the same as the writing is. Like if the base is positive, this is PNP, so the lower will be at lower, the base is negative, so it is good for the lower transistor, current flows to the lower IC2. Then when the IC2 flows, then if for class B operation, the upper transistor remains off. Upper transistor is not on. If the lower is on, then, and when the upper works, the current flow IC1, and then the lower becomes off. So each transistor works for one cycle, for one part of the cycle. Transistor generates the large harmonic contents like omega 2, omega 3, omega, but the push-pull connections cancels the even harmonics. So this is very good. This is the signal. Signal is varying like this. Now here there is a problem because for some part there is no collector current for some part. So therefore the signal, there come in the output signal there come a distortion. So sorry, now this is correct. So this is the distortion here. Some part of the signal is missed in the output. So this it is happened for the exact class B operation, and this is called crossover distortion. It is always present in the exact class B operation. Now, how the problem is overcome, this again a question. And the situation can be improved by the use of small forward biasing to the transistors as indicated, not below, above, that the some base current always flows very small, even in the absence of the signal, to eliminate the crossover distortions. And it is shown here in this figure, as well as it is, in the above circuit, the biasing which was applied to R1 and R2, it was because some small base current to flow even in the absence of signal. Then what happens? Look exactly for the input signal, how the output will appear now. So there are some base current IB1 and IB2. So collector current is now not exactly 0 for some time. So it is good, like it is advantage. There is no crossover distortion appearing now. There is no crossover distortion. Okay, this is IB2. So it happens because of the presence of some base currents. So crossover distortions are eliminated. That's very good. So small current is present in the transistor all the times. The operation is not exactly class B, it is approximately class B now. The bias is provided R1, R2 in the push-pull circuit, like here. Now we're coming to the efficiency of push-pull amplifier. The characteristics curves, and above is this load line of one transistor above, and below is the load line of the second transistor. Load line of T1 and below is the load line of T2. So this is for second transistor. The Imax. Now here we find the slope. Slope is perpendicular over base. And we take the inverse of. R dash is the exact load which is VCC over I max and equals to N1 over N2 whole square into R. R dash is the load. So output swing is a fraction of the Now lastly we are coming to the efficiency, output power of the DC power, and it comes out equals to pi k upon 4. Now substituting the values If we think that the maximum efficiency, then K equals to 1. It comes out 8.5%. Very good efficiency.